Okay, so Unit 1, Random Variable Probability Distribution. This is the Unit 1 of Probability and Statistics in University of Visayas Senior High School. So first, um, let us read this introduction. So statistics covers a wide range of topics with a lot of application in so many different fields. So in general, one can say that statistics is the method of analyzing data, which can either be quantitative or numerical, or qualitative or categorical, as transformed by research into number. So therefore, one word to explain statistics for me is data. So in statistics, it is not just about that. It is also include the whole process of using scientific method. So to answer questions that will help us in making decision. So these methods can be used in answering questions like what type and how much data are needed, of course, how are we going to organize the data, and how are we going to analyze and interpret the data. Next, what are the conclusions that can be drawn from the analyzed data. So based on these questions, we will define statistics as a branch of science that deals with the collection of data, presentation of data, analysis or analyzation of data, and interpretation of data. So as well as a given conclusion of the data if we are talking about inferential statistics that we will be discussing later. Okay. Next slide. Hold on. Okay. So there are two branches of statistics. First we got descriptive, and the second one we got inferential statistics. Okay, so descriptive statistics is concerned with collecting, describing, or presenting and giving analysis and subset of the data without drawing any conclusion or inferences about the set of data. On the other hand, inferential statistics is concerned with analysis of the subset of data leading to prediction or inference about the set of data. So therefore, in descriptive statistics, it's just merely giving description from gathering data, collecting data, collect, presenting data, um, analysis of the data or giving analysis and interpreting data, but without giving any conclusion. But in the other hand, inferential statistics, collecting, presenting, analyzing, interpreting, and giving conclusion or inferences as well. Um, okay, so the main purpose of inferential statistics is to make conclusions, generalization, prediction, or inferences about the entire set of data based on from a part of it. So there are two sets of data, the population and the sample. Those are two sets of data. The population is the entire set from which the sample is drawn, while the population is just the part of the sample is part of the population. So it is the set of all elements of the given observation units under study with at least one characteristics in common. So population may consist of but are not limited to people, animals, objects, or events. Yeah, that's true. Um, as what I said, population is part of the whole. Sample is part of the whole, or it's a part of the population. So, take the example, all grade 11 students enrolled in your school. So the sample drawn from the population is a subset of the population from which the data is collected. Yeah, example, all grade 11 student, that's your population, and then you're going to ask from the grade 11 students, I'm gonna get 10 students coming from different strand in all grade 11. So those 10 students in different strands, those are sample, while the all grade 11 is um, the population. But if we're talking about the entire school, let's just say the whole population in UV, and you just say let's try to have um, 10 students per department. So those 10 students per department, those are just a sample for the entire population in UV. Okay, so that is the difference between the sample and the population. So take note, those are two sets of data. Okay, so example, assuming that the population is one stated above, like the sample could be the grade 11 female students enrolled in your school, or it could be the grade 11 male students enrolled in your school. Let's just say, let's talk about all the students, okay, all the students in the school. So of course, if we're asking about only female students, then that is only a sample, because female students is part of the whole. Or in the other hand, you ask all the grade 11 students to go there, or to whatever it is. So those male students are just a sample from the population. Okay, so again, let's continue. So the numerical measure that describes the population of interest under study is called parameter. So while the numerical measure of the sample is called statistics. Again, the numerical measure that describes the population of interest under study is called parameter, while the numerical measure of the sample is called statistics. An example of parameter population stated above can be the average of height of grade 11 students enrolled in your school. Take a look. If you tried thesis or sort of BB thesis before, if you have what we call the survey method, then there is a sort of numbering, like 1, 2, 3, 4. 1 indicate as never, and 2 indicate is normal or poor or something like that. Normal, then it goes higher. So that would be parameter. So okay, so I'm sorry, earlier there's a customer behind me. Okay, so where are we now? Okay, so in relation to this, a statistic that will estimate a stated parameter would be the average of height of the grade 11 female students enrolled in your school. So statistics is like seeing a footprint, then guessing what type of creature produced it. But what if we don't know what footprint can a certain creature make? Yeah, that's one thing to need to be known first before we conduct research, right? How are we going to provide a good conclusion or interpretation if we don't know the problem yet? I mean, those things that need to be done. So the first thing first, we must know the basic, or what's need to be done first or known first. Okay, so next. So what if we're not familiar with that creature at all? So we should start first with finding out the creature first, then figuring out what footprint it will make. That's correct. So statistics start from gathering of data, so to making generalization about how things works. Unfortunately, without any idea about how things work, doing statistics will not be successful. From making generalization, then figuring out what type of data we're likely to obtain, and we will be able to understand statistics more. That is the job of probability. So probability provides justification for statistics. Take note for that. So probability provides justification for statistics. Okay. So lesson 1. Okay, so we're now in the first lesson, which is the basic concept of probability. So first we have a certain quote here from Rene Descartes. So it is a truth very certain that when it is not in our power to determine what is true, we ought to follow what is the most probable. Yeah, that's correct. Let's just say you are not you are from let's just say you're from the other room. Then when you entered a certain room, then somebody is laughing, then you will be also laughing, even though you don't know why are you laughing, because all of your classmates or most of your classmates are laughing. Yeah, that's really true. Okay, so let's continue. Okay, so learning outcomes. At the end of this lesson, the student will be able to explain the concept of a random experiment, sample space, and even an event. Second, we can be able to find the probability of the event. Okay, let's read some trivia. Okay, during the World War II, the American and British intelligence agencies collaborated with the United States Playing Card Company in creating special decks of cards and sent to American soldiers. So these cards were so unique because once they became wet, they peeled apart, and inside these cards were maps and held their Allied prisoners of war escape from German power camps or POW camps. Right? Wow, that's amazing, right? Okay, so let's have the first activity. So first, you're gonna get a partner and do the coin toss experiment. So we will have a coin toss experiment first. Then you need to record a number of heads or tails that will occur if you toss a coin. Find the probability of a coin toss. Okay, so we have three rounds here. The first round is you're gonna toss a coin for 10 times. The second round is toss a coin for 20 times, and the third round you're gonna toss a coin for 30 times. So you need to find your partner first, or meaning every group has 2 students. Okay, all right, so we're gonna need to have a sample data. Let's just imagine our first toss is let's just say head first. The next, let's have 10. Okay, so first we got head. Let's just assume that we got head, then we got tail, then we got tail again, then we got tail again, we got head again, head, then head again, then tail again, head, and head, 2, 4, 6, 8, 9, then head. So therefore we got, how many heads do we have? Okay, the number of heads is equal to 2, 4, 6. Let's just imagine like that. Then the number of tails, let's just put like this. Head is equal to 6, and tail is 4, of course. Then write the number in fraction form. So we got 6 over 10. We got 4 over 10. Okay, for the head, we get this 6 over 10. And for the tail, we get 4 over 10. Okay, so we just put equal sign here. No, not yet. Just like that. Okay. Next. Okay. So imagine we got. This is first round, okay? Second round. Let's just imagine we got this is 2020 toss coin. So let's just imagine we get 15 heads out of 20, and we get 5 tail only out of 20. Okay, and for the third round, let's just imagine we got 22 over 30 for the head, and the tail is 8 over 30. Okay, so let's just imagine like that. So we already done our experiment, then let's answer this question. So how many times did many times did the heads appear? Okay, so alright, if you're asking how many, for each and every one, we got 6, we got 15, we got 22. Then how about the tails? We got 4, we got 5, and we got 8. Okay, and then add a fraction from the outcomes of heads. So we get 6 over 10, 15 over 20, 22 over 30. You're gonna add up those one, and then add a fraction of the outcomes of tails. You're gonna add a fraction of the outcomes of tail. Okay, so no need to do that. So what do the results tells you or tell you? Okay, so the result tell me that the result tell me that in tossing a coin, therefore the head appears most compared to tail. But this is only my sample, so this is not really, I mean, not all the time this would happen, because there will be also a time that the tails would be much more chances compared to the heads. Okay, so that this is only my own observation. This is just only the result of my experiment. Okay, this is only it depends on who's the person who's trying to experiment this, so we can have a different answer. Okay, so we are all aware that statistics is very useful in mathematics, economics, banking, natural and social sciences, medicine, astronomy, and many other fields. For example, a businessman must be very quick and accurate in making decisions for his business to be successful. Alright, yeah, that's true. So statistics helps businessmen to determine which products to produce according to the taste of the buyers. Aside from the statistical, methods can be used to check the quality of the products more efficiently. Thus, all of the activities of a businessman are based on the statistical information. So this statistical information can be obtained with the use of experimentation. Yeah, this is definitely true, because I think the most of the successful businessmen, or not most but all, I guess, they're using data, they're using statistics in order for them to know what is much really or most needed in their business. So let's just example, I have an internet cafe, and let's just imagine that I have those customer gamers. Some are playing Dota, some playing League of Legends, some playing offline games. So I have those data, and let's just assume that it tells me that most of them plays Dota. So in order for me to give to give promotion to my internet shop, I'm gonna give maybe focusing on Dota, or not maybe but focusing on Dota and giving promotion, because most of my customer are playing Dota. So just like that, it's just an example. Okay, so 1.1, so random experiment and a sample space and event. So the coin toss experiment earlier is form of a random experiment. So a random experiment is an action or process that leads to one of several possible outcomes. That's correct. Here are some examples to illustrate a random experiment and their possible outcomes. Tossing a coin, casting a die, drawing a card from a standard deck of cards. So in a tossing a coin, there are two possible outcomes, the head and the tail. For casting a die, there are 6 possible outcomes, 1 to up to 6. And drawing a card from a standard deck of cards is 52. There are 13 clubs, 13 spades, 13 hearts, and 13 diamonds. From ace to king. Okay. So the outcome must be collectively exhaustive and mutually exclusive in order for us to know or to call it a random experiment. Okay, so what are those two things, these collectively exhaustive and mutually exclusive? If we're talking about collectively exhaustive, it means that all possible outcome or the possible outcomes must be included. Okay, so while mutually exclusive means that no outcome can occur at the same time. Let's just have an example for collectively exhaustive. If I gonna have let's just imagine a cube. Okay, so if I gonna ask you what is the probability of getting 7 in a pair of die or in a cube die, there is no possible answer. So meaning that is not collectively exhaustive. So meaning that is not that is a false, right? So meaning it should be the possible outcome must be included. So if I can ask you what is the possible outcome or probability that we get 2 in casting a die, so that is collectively exhaustive because 2 is part of the possible outcomes, right? So let's just imagine a deck of cards and I'm gonna ask you what is the probability of getting 15 of hearts. And as we know that there is no 15 of hearts in a deck of cards, so meaning that is not collectively exhaustive, right? So on the other hand, what is mutually exclusive is that it means that no outcomes can occur at the same time. So let's just imagine in a casting a die again, and again I ask you what is the in the 6 possible outcomes. Those are uniques, right? So there are no two twos or 2 threes there or 2 fours there. So meaning each and every possible outcomes occur only once, right? So okay, so we have an example here in our slides. So in a coin toss experiment that we did earlier, the outcomes head and tail are collectively exhaustive because they encompass the entire range of possible outcomes. So in other instance, it is impossible to have an outcome other than the 2 when tossing a coin. And when you toss a coin, the result will be either a head or a tail, but not both. That's true. Thus, we can say that the outcomes are mutually exclusive. So, in casting a die, are the outcomes collectively exhaustive? Of course, yes. Are they mutually exclusive? Yes. How about the outcome in drawing a card from a standard deck of cards? So yes, those are mutually exclusive and collectively exhaustive. So those 3 random experiment, they could be called random experiment because they fall on these 2 things. It should be mutually exclusive, and second, it should be collectively exhaustive. Okay, next. So each set of outcomes from each random experiment presented previously is an example of a sample space. So a sample space denoted as capital S of a random experiment is the list of all possible outcomes of the experiment. So S is equal to O1, O2, O3 until the OK, where O is called the sample point, or somehow we called outcome. The total number K, this K, this is the total number of the sample point. is called the cardinality of the sample space. So K stands for the cardinality of the sample space, or N of S. This is the number of sample space or the cardinality. Okay, so let's just count. That is the number of sample space or the cardinality. So in the coin toss experiment, we have two sample points. Yes, the head and the tail. Therefore, the cardinality of the sample space is also 2. Thus, N of S is equal to the cardinality, or the number of sample space is equal to the cardinality. So what is the sample space on toss coin? 2. What is the cardinality of toss coin? 2. What is the number of sample space of casting a dice? Casting a die? 6. What is the cardinality of casting a die? 6. What is the sample space of drawing deck of cards? 52. What is the cardinality of in a deck of cards? 52. So meaning the number of sample space is equal to the cardinality. Next. So look at this one. How many sample points do we have in a casting a die experiment? What is the cardinality of the sample space of drawing a card experiment? So I just answered it earlier. So let's have an example here. An event E, okay, take note. This is not an example, I'm sorry. So an event E is in any subset of the sample space consisting of one or more sample points to which a probability is assigned. An event is usually denoted by capital letters like A, B, E, or any letters in the English alphabet. So example, perform a random experiment by tossing a coin twice. Okay, so let's just have an example in tossing a coin twice. We will start here. Okay, when you toss a coin, there is two possible outcome. It could be head or it could be tail. So this is the first toss coin. Okay, our second toss coin, if you are here in the head, okay, let's just imagine you are here in the head. Okay, in your next toss coin, there are two possible outcomes also. It could be head or it could be tail. But what if you are in the tail? Then you also have two possible outcomes, the head or the tail. So therefore, from here, when you are tossing a coin, there are 4 possible outcomes: the head tail, the tail head, and the tail tail. So meaning you have 4 sample space. Okay, I mean there are 4 number of sample space, and your sample space are HH or the head tail head, and the tail tail. So event. Let's have an example or a problem or a question or an event. Okay, so the question, it asks us getting at least one head. Okay, what is the probability of getting at least one head? So look at the possible outcomes, because this is outcome 1, this is outcome 2, outcome 3, and outcome 4. So N of S is equal to 4. Okay, let's just write here. Okay, so our N of S here is equal to 4, or our cardinality is equal to 4, and our sample space is HH, HT, TH, and TT. Okay, so our event here is getting at least one head. Okay, getting at least one head, something like that. Alright, so which of the following has this characteristic? At least one head. At least one head? Yes, of course, because there are 2 heads here. So at least one head, meaning if we have 2 heads here, so it is true, or it is included, right? Here, at least one head, this is also included. Here, of course, and here, not, because there are 2 tails here and nothing is head in the 4th outcome. So therefore, our event or event is equal to, so these are your outcome event. Okay, so those three are your event. Okay, so number of event is equal to 3, right? So that is the number of event is equal to 3. Okay, now let's continue. So understanding the concept of a random experiment, sample space, and event. Okay, it is very important so that we can compute the probability of an event. So probability is a numerical measure of the likelihood of the occurrence of an event. The probability of the occurrence of an event, P of E, has the following properties. Okay, so P of E is greater than or equal to 0, and P of E is less than or equal to 1, in which P of E it will equal to 1 if the event cannot occur. That's true. Okay, second, for this number 1, P of E is equal to 1 if the event occurs every time, or 100%. See, otherwise the probability is a fraction between 0 to 1. Okay, always remember that a probability is from 0 to 1 only. If you put 1.1 or 1.001 or whatever it is, then it is not considered as probability. Take note, probability start from 0 until 1 only. 0 until 1. So 2, the summation, this sigma symbol here, or Greek letter here, it is meaning summation. So summation of P of E is equal to 1, or the summation of P alternate, I forgot the P, what is the meaning of that? Here it is, complementary. So summation of P complement of E is equal to 1. So this means that the least of all outcomes must be a non-overlapping set of events that includes all the possible outcomes. Okay, 3. So P of E plus the P complement A is equal to 1. Of course, let's just say, what is the complement of, in order for it to become 1? Okay, since the probability should become 100% from 0 to 100%. So the total number, or the total number of probability is only 100%. So what would be the complement of that certain number to it that will become 100%? Let's just imagine 1/2. What is the complement of 1/2 in order for it to become 1? Of course, 1/2 also. Okay, so how about 1/3, 1/4, 3/4, right? So that is the complement of a certain number in order it to become 1. Okay, so this is known as the complementary probability. So the complement of event A is the event that occurs when an event A does not occur. So the complement of event A is denoted by P complement of A, and the complement rule is based from the fact that the probability of an event and the probability of the event's complement must be equal to 1. Hence, the complement rule can be written as P complement of A is equal to 1 minus the P of A for an event of A. That's correct, right? If we would try to look for the complement of A, right, we just deduct the probability of the event from 1. So in order for us to know what is the complement, the probability of complement A. Okay, so now shall we consider the two ways of assigning the probability? So we're on the two ways of assigning probability. Okay, probability of an event. So these are classical probability. First, we got classical probability. Psych probability approach. Second, we got empirical probability. Empirical. Oh man. Probability approach. Okay. Or somehow we call this one frequency relative approach. Okay, so the classical probability approach of assigning probability of an event is used to determine the probability associated with games of chance. In this approach, there are two assumptions. So meaning in classical approach, we are focusing in the games of chance. Okay, so we are dealing with some of gambling, I guess, or some games here in classical probability approach. So these are two assumptions. First, the outcome must be mutually exclusive. If we say mutually exclusive, the outcome should the outcome should not appear twice, so it should be only one or once only. Okay, while the second assumption, the outcome are equally likely to occur. Of course, it should be equally to occur. Let's just say it's just the same with mutually exclusive, because it could not become twice, and of course it should be equally likely to occur those possible outcome. Okay, so it's just connected. Okay, for instance, in tossing a coin, we can use the classical approach in assigning the probability of getting a head or a tail, because the outcome are mutually exclusive as stated before, and they are equally likely to occur. But yeah, so since the sum of their probability is equal to 1, so of course P of H plus P of T is equal to 1, because everything should be equal to 100%. The all possible outcomes should be 100% or equal to 1. And the probabilities are equal to each other. Yes, because P of H and P of T are just, if you add it up, it will equal to 1. So meaning P of H is equal to one half, and P of T is equal to 1/2, and they're equally to occur, right? They're equally likely to occur. So the two outcomes have 1/2 probability or chance to appear or to occur. Okay, next, if all possible So if all possible outcomes can be listed and the occurrence of each outcome is equally likely, then we can compute the probability of the event using the formula P of E is equal to N of E over N of S. So P of E, this P of E's probability of the event is equal to N of E. P of E is equal to N of E over N of S, where P of E stands for the probability of event, while N of E is the number of event, or the quantity of the event, or the occurrence of event in the sample space, and the N of S is the number of sample space, or somehow we call the cardinality of sample space. Okay, so example number 1, find the probability of getting exactly 2 heads when tossing a coin twice. As what we done earlier in creating a tree diagram, we could have these outcome HH, HT, TH, and TT. Those are 4 possible outcomes. So solution. So let's let S is the number of the sample space. So S is equal to head head, head tail, tail head, and tail tail. So the question in the event, getting exactly 2 heads when tossing a coin twice. As what can you see about the outcome? There is only one possible outcome that it will appear out of 4, meaning the number of event is only one, right? Only one. And the number of sample space are 4. So therefore, the P of E is equal to the N of E is 1, and the N of S is 4. It is equal to 0.25, or if we try to convert it into percentage, it's 25%. So the answer is the probability of getting exactly 2 heads when a coin is tossed twice is 1/4, or 25%, or 0.25. Okay, so that would be the answer for number 1. Example number 2. Find the probability of drawing a face card from the standard deck of cards. Okay, so the question asks us about cards, and it talks about drawing a face card. If you remember, a card has 52 cards, right? From ace to number 10 to jack to queen and to king. So if you notice, the face card or cards that has a face are jack, queen, and king. Okay, and we get 4 jack, okay, 4 queens, and 4 kings, like club, jack club, J club, spade, J spade, J heart, and J diamond, right? So there are 4 jacks, 4 queens, and 4 kings. So therefore, we have the N of E, I mean, for all of these is 12, right? I don't want to confuse you, so let's just have this one. Jack club, J club. Okay. Here it is. I already done this here. So event, because it asks us drawing a face card and a standard deck of cards. So solution, since there are 52 cards in standard deck of cards, then the N of S is 52. That's true. Event is drawing a face card from the standard deck of cards, and how many face cards are there? So the event with the face cards, these are J diamond, queen diamond, king diamond, J heart, Q heart, king heart, J club, Q club, king club, J club, queen spade, king spade. Okay, so meaning there are 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the number of E, or the number of event, is 12 because there are 12 face cards, and the number of sample space is 52 because in an entire deck of cards there are 52. If you try to get the lower term, lowest term rather, it's 3/13, or approximately 23%. So the answer is the probability of drawing a face card from 52 cards is 3/13, or approximately 23%. Okay, next. So computing for probability of an event will be easier if a total number of possible outcomes are known. Of course, it's pretty hard if you don't know the number of outcomes in a certain data or in a certain problem. If you don't know the possible outcome, if you don't know what is club, you don't know what is spade, you don't know what that in an entire deck of cards is over 52, then it's quite hard for you. So first thing first, you need to know the need to be known first, okay? Especially the number of sample space. So to determine the total number of possible outcomes in a random experiment, counting techniques may be used. Of course, you need to count. First, we get fundamental counting principle. So in a sequence of events, the total possible number of ways all events can be performed with the product of the possible number of ways each individual event can be performed. Second, we also have permutation. So a permutation is an arrangement of objects without repetition. Repetition and per order is important. So a permutation of n objects arranged in group of size R without repetition and where order is important is. So the NPR, and the next of these is the combination. For permutation, this is the formula. NPR is equal to P of NR, in which N is the number of object and the R is the size of each permutation, equal to the N factorial over the quantity of N minus R factorial. Okay, so next we got combination. So N factorial over the quantity of N minus R factorial multiplied to R factorial. So yeah, I know that you already done this in your grade 10. So in this topic or lesson, we are not going to focus on permutation and combination. Okay, let's just have a sort of I know that you know those things already. Okay, so the second approach of assigning the probability of an event is okay. So the second approach of assigning probability is the empirical approach, or also known as the relative frequency approach. So first we have the classical approach, then the second one we got relative frequency approach. So this method is finding probability that is based from the cumulative historical data or found through the observation and not from theories. Okay, so that is the difference between the classical. If the classical probability approach is about or focusing on the game of chance, in empirical or relative frequency approach, it's based on the cumulated historical data or an observation and not from theories. Okay, so for example, the chance that it will rain today is 80% because it rained for 4 days. So that is a sort of having an observation. So imagine there are 5 days and today is the 5th day, and for the first few days, the first 4 days, it rained. Okay, so you are trying to guess that today it will rain about 80% because 4 out of 5 it happens that it rained in the first 4 days. So that is a sort of 80%. So that is somehow we call an empirical approach. It is basing on the historical data or a certain observation. So this is the formula, or this is the form. P of E is equal to N of E over capital N. N is the total number of opportunities for the event to occur. So, but if you try to analyze classical approach and relative frequency approach, is in terms of knowing the answer and having a formula, it's just sort of the same, but the things or the description or about the what happened, that is the only thing that differ from each other. Okay, so example number 1. In his entire career, a certain PBA player hooped 4,503 out of 6,575 free throws. So what is the probability that his next free throw will be successful? Okay, so solution. P of E is equal to N of E over capital N. So yeah, that's true. The free throw, that is the solution is here. This 6575 here is the total number of free throws that he made, or he attempted, while this 4503 is the counted, or the player hoops for 4503. Okay, so just this is your number of event and this is the number of the entire free throws, or the entire happening, or the entire attempt. So you divide it, you got 68.49. So the probability that the PBA player's next free throw will be successful is approximately 68.49%. The only thing difference there is the description, or the things that, or about the problem. It talks about the past happening, or some sort of historical data. So meaning it is relative frequency approach or empirical approach. If this is a game of chance, then this is a classical approach. So those are the only thing differ from each other. Example number 2. If you cast a pair die 25 times and 8 of them result in a 6, what is the empirical probability observed in this event? Of course, you cast 25 times and then 8 of them is 6. So what is the empirical probability observed in this event? So 8 over 25 is 32%. So it talks about the previous happening, talks about the observation, so meaning this is empirical approach. So the probability of getting a 6 is 32%. Okay, next. So let's have a summary. Okay, so random experiment is an action or process that leads to one of several possible outcome is an action or process that leads to one of several possible outcomes. Sample space, denoted as capital S, is a list of all possible outcomes of an experiment. Sample point is individual outcome of an experiment. Event is any subset of the sample space consisting of one or more sample points to which a probability is assigned. Probability is a numerical measure of the likelihood of the occurrence of an event. And the last one is the classical approach, is used to determine the probability associated with games of chance, and it is denoted by the formula P of E is equal to N of E over N of S. While the empirical approach, or the relative frequency approach, is a method of finding the probability that is based from accumulated historical data or found through observation and not from theories. It is denoted by the formula P of E is equal to N of E over capital letter N, or capital N. Okay, so that would be the end of our first lesson about the random variable and probability distribution. Okay, so do the right thing for the right things. Even the right thing might not be the good thing. So, pasensya na. Why? Naglisod ko English. Pulig in English.